This is 4x1 multiplexers, or sometimes we can call it as 4x1 MUX. 4 is nothing but input line and 1 is nothing but output line, and this multiplexers we can represent with one block like this. So this is 4x1 MUX, right? As we are having 4 input lines, I'll assume I0, I1, I2, I3 are the input lines, and single output, let's take Y as the output line. So to transfer this data from input to output, we require selection lines, right? For the selection lines, we have a relation, that is what? N equal to 2 power m, where n is what? Input lines, 4. To satisfy this equation, we can write 2 square is nothing but 4. So from this, m is nothing but 2. So for 4x1 MUX, we require 2 selection lines. Let's take S0 and S1. For each combination of these selection lines, input data will be transferred to output Y. In addition to these input, output and selection lines, there is a one more is required, that is E, called enable. Here output will be transferred only when enable is high. If enable is low, this 4x1 MUX is in off condition. Okay, right. Now the thing is, we need to design the logic diagram which is there in this 4x1 MUX, or which exists in this 4x1 MUX. To get the logic diagram, first we need to develop a truth table for this circuit. Right. To develop the truth table, we'll consider the input, what is it is E, and S1, S0 are the input lines, and we need to find what is output Y, right? For the first case, I'll assume enable is 0. Enable is 0, right? When enable is 0, as I already told to you, irrespective of this selection lines, means whatever it may be, so whatever it may be, your output is always 0. Okay, there is no effect of this selection lines when enable is 0. For the next case, I'll make this enable as high. For the remaining all cases, I am assuming this enable as high. Then we'll see how the data will be transferred. So for the first combination, let's take 0, 0 combination. If these two are 0, 0, means selection line value is 0, 0, then I0 data will be transferred to Y. Okay. Next, for the next combination of S1, S0, let's take 0, 1 combination. I1 data will be transferred to the Y. For the next, let's take 1, 0 combination. For 1, 0 combination, I2 data will be transferred as a output. For 1, 1 combination, if S1 and S0 are 1, 1, I3 data will be transferred to the output. So in this way, for each combination of selection lines, only one input data is transferred to the output, right? So as you know the truth table, from this truth table, we can find the logic expression for this 4x1 multiplexers. We'll write the logic expression only when output is exists, means for these cases itself. When output is 0, no need to write the logic expression for this. Okay. So I am considering only these cases in SOP form. So for the first case, E is high. So I am considering E. These two selection lines are 0. So I can consider it as S1 bar and S0 bar. Okay. And output is what? I0. So this is one possibility to get the output value. That is what I0 as a output value. Or we can get output also, I1 as a output also, right? So or one more possibility is what? E. See, for all these cases, E as high. Okay. So E, S1 bar, S0 and I1. Or there is a one more possibility. I2 is also output, right? So when E, S1, S0 bar and I2 plus fourth possibility is what? E, S1, S0 and I3. 0 I am considering it as a complement form. 1 I am considering uncomplemented form because we are considering SOP, right? So now I got the logic expression, but in these terms E as common. Let's take E as common. So we can write it is S1 bar, S0 bar, I0 plus S1 bar, S0, I1 plus S1, S0 bar, I2 plus S1, S0, I3. This is a logic expression for 4x1 MUX. As I know the logic expression, so I can implement logic diagram. See, E is common here, so I will consider later. I will first draw this logic, only this expression. Here we are having inputs are I1, I2, I3, I0 and two selection lines. So I am considering all the values S1, S0, I0, I1, I2, I3, right? Fine. But in some terms, S1 and S0 are in complemented form. So I am giving one NOT gate to this inputs so that I will get S1 bar. I will give one NOT gate to this input so that I can get S0 bar. Okay. Now we will develop each term. In this first term, we will have S1 bar, S0 bar and I0. So S0 bar, S1 bar and I0, which are given to one AND gate. And the second term is S1 bar, S0, I1. So S1 bar, S0 and I1 given to one more AND gate. And third one is S1, S0 bar, I2, S1, S0 bar and this is I2, give it to one more AND gate. And fourth term is S1, S0, I3. So S1, S0 and I3, give it to one more AND gate, right? And all the terms are OR together. So consider one OR gate here. This This is y. Connect all the outputs here, right? Here the first term I am representing, this one is what? S1 bar, S0 bar, I0. This one, S1 bar, S0, I1. And this is S1, S0 bar, I2, S1, S0, I3. Right? Now this term is over. Now this is ANDed with E. So I need to take a common input, that is enable. Right? Connect to all the here the enable value always must be equal to high. Right? Now the block diagram consists of this logic diagram inbuilt in this MUX. Okay. Similarly, we can implement 8x1 MUX also. We'll see how it is. This is 8x1 multiplexer, or we can call it as 8x1 MUX. 8x1 means 8 inputs and 1 output. This 8x1 MUX we can represent with one block diagram like this. 8x1 MUX. As in 8 input lines we are having, take 8 input lines, I0, I1, I2, I3, I4, I5, I6, I7 are 8 input lines, and one output line is Y. Right? So 8 input lines and one output line. To direct each input to the output, we require a selection lines. A relation between selection line and input line is n equal to 2 power m, where n is input lines, nothing but 8. M is selection lines. Here you just see 8 we can write as a 2 cube. Right. So this 3 is nothing but m value, that is 3 selection lines are required. Let's take S0, S1 and S2 are the 3 selection lines. Right. In addition to this, we'll have one more line, that is called enable. Generally we'll represent with E. The purpose of enable is, it is like a switch. If enable is 0, this entire MUX is in off condition. Okay. Means whatever may be the selection line value, the output transferred is always equal to 0. When enable is high, this circuit is in on condition. Okay. Now the thing is, we need to find the inbuilt circuit which exists in this block. To find that logic diagram, we need to find the logic expression. That logic expression is always obtained from truth table itself. So first I'll develop the truth table. For this. Okay. So for the truth table, here we are having the input possible combinations are E, S2, S1 and S0, and output as Y. Okay, fine. Now for the first case, I'll consider enable is 0. So when enable is 0, irrespective of your selection lines, data transfer to the output is 0. Okay. So for the remaining all cases, next I will make this enable as high, nothing but 1. For all possible combinations, I am considering this enable 1. Now, for the first case, I will consider all the selection lines are 0. So during that case, I0 data will be transferred to Y. So output is what? I0 itself. Whatever the data which is present in I0, that is transferred to the Y. I0 may be a 0 or 1. So I am representing I0 itself. Okay. For the next possible combination, what it is? For 0, 0, 1 combination of selection lines, I1 data will be transferred. Okay. Next, for 0, 1, 0 combination, I2 data will be transferred. For the next combination, that is what? 0, 1, 1, I3 data will be transferred. For 1, 0, 0 combination, I4 is transferred. For 1, 0, 1, I5 is transferred. For 1, 1, 0, I6 data is transferred. For 1, 1, 1, I7 is transferred. So for each combination of selection line, one of the input is transferred to output. Right. Now I know the truth table. From this truth table, we need to find the logic expression for 8x1 MUX. Right. We'll consider output only. It has some value. If it is 0, no need to consider. So I am considering only these cases, right? For all these cases, as enable is common, I am taking E as common directly. And for the first case, the input value is what? S2 bar, S1 bar, S0 bar. Means all are 0. Then I0 will be transferred, right? That is the first thing. Or if this case is not, then we'll go for this. That is what? S2 bar, S1 bar and S0. Then what will happen? I1 will be transferred. Or there is a one more possibility. I'll write here itself for each combination. This is S2 bar, S1 bar and S0. I1 will be transferred. Or the third case I am writing here, it is what? S2 bar, S1, S0 bar, I2 data will be transferred. S2 bar, S1, S0 means for this combination, I3 will be transferred. Or for the next combination, if it is S2, S1 bar, S0 bar, then I4 will be transferred. Or for this combination, I can write it as S2, S1 bar, S0, I5 will be transferred. For the next, S2, S1, S0 bar, I6 will be transferred. For the next combination, S2, S1, S0, I7 will be transferred. So this is logic expression for each selection line combination. As I know the logic expression, I can develop the logic diagram. To develop the logic diagram, here you just see what are the possible input lines we are having. Here we are having 8 input lines, I0 to I7, that we need to take, and all the selection lines and one common input enable, right? So I am taking the selection lines here. Let's take S2, S1 and S0. Okay, and these selection lines are in complemented and uncomplemented form. So to get the complemented form, I am using a NOT gate here itself. So S2 bar, S1 bar, S0 bar. In addition to this, I am considering enable also here itself because enable is also common to all. Fine. Right. Now, the first term is what? S2 bar. So, I am taking S2 bar. See, when we are drawing the logic diagram, you have to remember if there is a dot, then only there is a connection. Though it is crossing all the lines, but there is no sense of it. Only dot means there is a connection. Okay, fine. S2 bar, then we'll have S1 bar, S0 bar, and I am taking I0 here itself. Let's take I0 and enable E. So give it to 1 and gate. Then the next term will be S2 bar and S1 bar, S0, enable and I1. Right? The next one is S2 bar, S1 and S0 bar and I2, give it to enable. Right? The fourth term is S2 bar, S2 bar, S1, S0, I3. So S1, S0 and enable I3. I am taking I3 here itself. Give it to 1 AND gate. And the next term is S2, right? S2, S1 bar, S0 bar, see S0 bar, and I4 I am writing I4 here itself, and enable E is common for all. This is my fifth combination. We'll have this one is S2. So I'm taking S2, S1 bar, S1 bar, and see S0, I5. So S0, I am taking I5 here itself and common input E. Give it to 1 AND gate, and the next term is S2, S1, S0 bar and I6. In addition to this, enable, give it to 1 AND gate. And the final term is S2, right? S2, S1, S0 and enable plus I7. Okay. Now all, just see 1, 2, 3, 4, 5, 6, 7, 8 terms. 1, 2, 3, 4, 5, 6, 7, 8 terms are given, are OR together. So I am considering one OR gate here. This is my overall output. Give it to this. Right? And this logic diagram exists in block diagram of 8x1 MUX. Right? In this way, we can implement 16 cross 1 MUX, 32 cross 1 MUX, 64 cross 1 MUX, like that.